starting with your notes packet for 6-1, there's a warm-up. On this warm-up, you have a choice of how you want to use this video. You could pause it right now and try each of the questions and then come back and check it for answers. You could stay with me and keep the video going through the first one and then pause it, go do the other ones yourself, and then come back and check. Or you can stay with me for the whole video if you need to. So the question that's asked is the ordered pair a solution of the equation that they provided, the 2x minus 3y equals 5 equation? So to tell, much like we did with inequalities, we need to see if when we put in the values of 1 and 0 for x and y, if it makes the equation true. If it makes the equation true, it's a solution. So if you want to pause the video now and try all 4 and then come back to it, go ahead and do that. Otherwise, stay with me and we'll work each one through. Please make sure you're doing this in your notes packet so I can see it when I'm back. So for the first one, I would take the equation 2x minus 3y equals 5, and I'm simply going to replace the x with a 1 and the y with the 0. So I'm checking if 2 multiplied by 1 minus 3 multiplied by 0 is equal to 5. What I know is that 2 times 1 is 2, 3 times 0 is 0, and 2 minus 0 is not equal to 5. So if the question is 1, 0 a solution to the equation, the answer is no. At this point, if you think you know what you're doing, you could pause the video and work on it yourself and then come back and check. Ignore that moving. Or you can stay with me and keep working them through. Now we're going to check for negative 1, 1 for problem number 2. So again, I'm going to use the original equation and check to see if twice the x value of negative 1 minus 3 times the y value of 1 is 5. When I calculate 2 times negative 1, that's going to be negative 2 minus 3 times 1 is 3 is not equal to 5. We actually have negative 5 on the left-hand side. So again, the answer to this would be a no. If I graphed the equation that's represented here, neither of these points would fall on the line. Again, to number 3, I'm going to check by plugging them in. If they satisfy it, they'd be on the line that's graphed. They'd be a solution to the equation. So twice positive 1 minus 3 times negative 1 for the third example, and I'm checking to see if that's equal to 5. 2 times 1 is 2, minus negative 3, and some of you like to do keep, change, flip, so that'd be 2 plus 3, 5. Yes, 5 is equal to 5, so this ordered pair would be a solution to the equation. Checking the final one, again, pause the video if you can test this out yourself, and then come back to it to see. We're checking if twice 4 minus 3 times an input of 1 is 5. So we're seeing if 8 minus 3 is 5. It does make the equation true, therefore it is a solution. So you'd answer yes. The reason we're doing this is this leads into some of the math that we're going to be doing in this chapter for chapter 6. It brings back some background skill. So in chapter 6, we're going to start talking about not only one equation, but actually 2 at the same time. So if I graph 2 equations, I might get 2 lines on my graph. So I pulled a map of part of Milwaukee, and maybe you know this neighborhood. If you don't, that's okay. Your graph's a little light, so you might want to darken some of the roads, but you can use the video to help. So to understand where we're going and what we're talking about, we're going to look on a map to see the different ways that certain situations could occur. So again, pause the video each time I ask a question if you want to make the most of your learning so that you see if you're understanding as you go, and then start it up again after you write down your idea and see how it compares. It says, how many ways could I be on 51st Street? So I'm going to find 51st Street and darken that for you in case yours is a little light. So 51st Street starts right here on your map, comes up like this, and actually does keep going past there. And on Loomis Road. And Loomis Road on your map is right here. So how many ways could I be on both roads at the same time? And if you look at the map and you look at what I have, there's one place, the intersection where the 2 come together. There is one location where I could be on both roads at the same time. I'm going to take those roads out so we can do the next one. The next one asks us, how many different ways can I be both on Edgerton Avenue and on Grange Avenue? So Edgerton Avenue on your map is right there at the top. So that would represent maybe one equation being graphed on a graph. West Grange Avenue is down here. They look parallel to me, and in fact they were built to be parallel to one another. That's how Milwaukee's roads were arranged. So the question about how can I be on both Edgerton and Grange at the same time, how many ways? There are 0 locations where I can be on both at the same time. And it was an and question, so it's not about one or the other. There are 0 locations that allow me to. In other words, those two roads never cross. They never intersect, so there's no intersection where I can be on both at the same time. And finally, it asks where I could be on Loomis and on Highway 36 at the same time. So Loomis is right here, but if you notice, it's also labeled as Highway 36. That's another name for that road. So if I were to put in a line for Highway 36, it would be right on top of the one I had just put in for Loomis. So how many different ways can I be both on Loomis and on Highway 36? Well, I can't even begin to count all the different places. So in math, we would say, well, there's infinitely many places that I could be on both roads at the same time. What this relates to is the number of ways we could graph 2 lines on a graph and have them intersect. They could intersect once, like our 51st Street and Loomis Road example. So please draw these in next to you so you get the idea. They could intersect 0 times and be parallel. In other words, they would never cross. Or they could actually be physically on top of each other so that there's really only one line appearing, just like Highway 36 and Loomis Road, and there would be lots of places that they would intersect because they would fall, every single point that's on one of them is on the other. So what we're trying to get at, and I'm going to end this video soon to make them shorter, is we're trying to talk about when 2 or more equations are graphed, or when 2 or more equations are considered at the same time. So when you flip to this part of your notes, let's just fill in this top box. 2 or more lines, linear equations, involving the same variables form what's called a system of equations. A system of equations could have 2 equations, 3 equations, 4 equations. They all have to use the same x and y. So if I'm asking for a solution of the system of equations, what I'm looking for is an ordered pair, a location. So when we say ordered pair, I'm looking for a location on my graph that works for both equations, that satisfies both, that makes them both work. On our map, I was looking for a place where I could be both on Loomis and on 51st Street at the same time, and there was a location. Any XY where graphs intersect, think intersection like our roads, that ordered pair would be a solution to the system. At this point, I'm going to go back to the graphs for a second, but you can keep looking at this box of information. So if our 2 equations graphed as 2 separate lines that happen to intersect once, I would report that one ordered pair and say that ordered pair makes them both work. If our 2 lines were graphed and they had no points in common, then I would say that there's no ordered pair that makes them both true at the same time. And if my lines graphed on top of each other, I would say there were lots of places where my 2 equations could be true at the same time. So the very last thing we're going to do in this is draw what that would look like on your graphs. So if I have 2 equations that I'm trying to solve at the same time, they might be 2 separate requirements for something. I have 3 possibilities of what could happen. So when I graph 2 equations, they might look like. So I'm going to draw this in and you can add them. It doesn't have to be my exact points that you hit. But somewhere on our graph, we could see one line graphed, we could see a second line graphed, and we could see exactly one place where those 2 equations, just like roads, could come together and have a solution So there'd be exactly one solution where they intersect. Some lines do that. There could be no solution, so I'm going to draw a quick picture of that over on the no solution side, meaning I graph two lines and they never head towards each other, they remain parallel, and they are never going to cross. So there's no place in common, no intersection for those roads, so there's no place I can be and satisfy both at the same time. So I'd have to say no solution if my graph looked like that. Or, if I went to graph something, and after I made the graph and I went to graph the second equation landed right on top of the first one, point for point for point, then there'd be many solutions, many places. This point satisfies it, this point satisfies it, this point satisfies both, because it works for both equations. Then there are infinite or many solutions, more than I could count. At this point, you're going to stop this video and switch over to the second one, but take a stretch for a second.